Since Newton saw an apple fall from a tree, we've thought of gravity as a constant, predictable force. 9.8 meters per second squared. That's the acceleration that glues us to the ground, makes rivers flow and leaves fall. But what if I told you there are places on our planet where this fundamental force of nature seems to break the rules? Today we're exploring the most extraordinary places on Earth, locations where balls roll uphill, where water defies logic, and where your own perception of reality will be questioned. Welcome to the points where gravity doesn't work like it should. Before we dive into the mysteries, we need to understand what gravity really is. Earth isn't a perfect sphere. It's an ellipsoid, flattened at the poles and bulging at the equator. This means gravitational force isn't exactly equal everywhere. NASA and ESA scientists have mapped every inch of Earth's gravity using ultra-sensitive satellites. What they found was fascinating. Gravity varies by up to 0.5% from one place to another. It may not sound like much, but it's enough to create extraordinary phenomena. Three main factors influence these variations. First, altitude. The higher you go, the weaker the pull. On Mount Everest, you weigh about half a kilogram less than at sea level. Second, latitude. Due to Earth's rotation, there's a greater centrifugal force at the equator than at the poles. And third, the density of the rocks beneath you. Mountains, oceans, and mineral deposits all create small variations in the gravitational field. But there are locations where something more is happening, places where the laws of physics seem written in a different language. Our first destination? The mysterious hills of California. Hidden in the sequoia forests of Santa Cruz, California, there's a circle about 46 meters in diameter, where the laws of gravity apparently don't apply. Discovered in 1939 by a group of surveyors, the mystery spot has become one of the world's biggest gravitational anomaly attractions. Inside this magic circle, people appear to stand at 45-degree angles. Balls roll uphill, brooms balance without any support. You can lean forward at angles that anywhere else would make you fall flat on your face. Even stranger, people's apparent height changes dramatically depending on where they're standing within the circle. People always ask if it's real or just an illusion. The answer is you have to come feel it for yourself. Your body knows when something's wrong. Your inner ear, your sense of balance. Everything gets confused here. It's not just what you see, it's what you feel. Over the decades, dozens of theories have tried to explain the phenomenon. Some believe in a gravitational anomaly caused by a cone of metal or magnetic mineral buried at the site. Others suggest the presence of radiation fields or even extraterrestrial influences. But official science points to something equally fascinating: a perfectly orchestrated perspective illusion created by nature. Researchers discovered that the mystery spot is built on terrain with a subtle but consistent incline. The surrounding trees, affected by years of wind and irregular growth, lean at specific angles that confuse our vestibular system, the internal mechanism that keeps our balance. Without a clear horizontal reference line, our brain literally can't distinguish what is vertical from what is not. When you use a carpenter's level or a plumb line at the mystery spot, they work perfectly normally. Gravity is pulling exactly as it should. The trick is how our perception is manipulated by the tilted environment and carefully positioned structures. But does this make the phenomenon any less impressive? Not at all. The mystery spot teaches us something profound about the nature of reality. Our senses, however reliable they seem, can be completely deceived. What we perceive as up or down isn't an absolute truth, but a construction of our brain based on visual and physical cues. And when these cues are manipulated, reality becomes malleable. About 1,000 kilometers to the north, in Moncton, New Brunswick, there's another phenomenon that defies logic. Magnetic Hill is a road where cars in neutral appear to roll uphill, defying gravity. The experience is simple, but profoundly unsettling. You park your car at the indicated point, put it in neutral, and take your foot off the brake. Then, slowly, your 2-ton vehicle begins moving backward, climbing what appears to be a hill. Tourists describe the experience as unbelievable. People say they didn't believe it until they saw it with their own eyes, cars literally going up the hill by themselves. The feeling is bizarre. Your brain tells you you're going down, but you're going up. It's like the world is upside down. Discovered in the 1930s, Magnetic Hill quickly became a sensation. In the early decades, people genuinely believed there was some kind of magnetic or gravitational anomaly at the location. Scientists came from prestigious universities to study the phenomenon. Theories included massive iron ore deposits, variations in Earth's magnetic field, and even faults in the Earth's crust. Experiments were conducted, compasses were tested, and they worked normally. Gravitational measurements were made, and they showed nothing abnormal. Geological analyses of the subsoil found no significant magnetic deposits. So what was happening? The answer is one of nature's most perfect optical illusions. Magnetic Hill is what scientists call a gravity hill, a type of illusion where the configuration of the horizon makes a gentle descent appear to be an ascent. Detailed topographic studies revealed that what looks like an upward hill is actually a very gentle descent. The illusion is created by the arrangement of trees, buildings, and surrounding hills that block the true horizon. Your brain, desperately searching for a horizontal reference line, uses the slope of the roads and surrounding structures, which in this case are all slightly tilted in the opposite direction. Magnetic Hill isn't unique. There are hundreds of gravity hills around the world, in Scotland, Italy, Australia, India, and dozens of other countries, each with its own set of local legends and supernatural explanations. In some places, people believe they are points of spiritual energy. In others, they believe they are portals to other dimensions. But when you place a water level on the ground or use precision GPS, the truth is revealed. Gravity is working exactly as it should. It's our eyes, our perception, that are deceiving us. These places remind us that our understanding of the world is shaped by the tools we use to measure it, and our most basic tool, our own perception, can be flawed. What we see isn't always what's real. Forget everything you think you know about illusions. Let's talk about something real, something extraordinary. Welcome to Hudson Bay, Canada, home to the largest known gravitational anomaly on the planet. Here, gravity isn't an illusion, it is measurably weaker. NASA's GRACE mission satellites mapped Earth's gravitational field with stunning precision. What they found in Hudson Bay was a shock. Gravity here is about 0.005% weaker than the global average. That might sound tiny, but in geophysical terms, it's a cosmic shout and a universal whisper. The reason is incredible, and takes us on a journey through geological time. During the last ice age, which ended about 10,000 years ago, an ice sheet more than 3 kilometers thick covered this entire region. The colossal weight of this ice, we're talking trillions of tons, literally pushed down the Earth's crust, squashing the viscous mantle below. When the ice melted, the land began its slow recovery, a rebound to its original position in a process called post-glacial rebound. But here's the catch. This process is incredibly slow. The crust is rising at only about 1 centimeter per year, meaning the region hasn't fully bounced back yet. With less mass concentrated in this depressed crust, there's less gravitational pull. It's a real mass deficit. If you brought an ultra-precise lab scale to Hudson Bay, you would genuinely weigh a few grams less than you would elsewhere at the same altitude. Scientists estimate it will take another 5,000 years for the region to fully recover and for gravity to return to normal. Until then, Hudson Bay remains a living testament to the immense power of ice ages, a place where the distant past is still shaping our present in very real, measurable ways. Now let's travel to the Peruvian Andes, where Mount Nevado Huascarán soars to 6,768 meters. This isn't the highest point on Earth relative to sea level. That honor goes to Everest. But it is the point on Earth's surface farthest from the center of our planet. How is that possible? Well, remember, Earth isn't a perfect sphere. Its rotation causes it to bulge at the equator and flatten at the poles. The equatorial radius is about 21 kilometers greater than the polar radius. Huascarán, located just 9 degrees south of the equator, takes full advantage of this equatorial bulge. Measured from Earth's center, Huascarán's peak stands at 6,384 kilometers, about 2 kilometers farther out than Everest's summit. This extra distance from the planet's core means something crucial: slightly weaker gravity. According to Newton's law of universal gravitation, the force of gravity is inversely proportional to the square of the distance. The farther you are from the center of mass, the weaker the attraction. Combine this with the centrifugal force from Earth's rotation, which is strongest at the equator, and you have the perfect recipe for the weakest surface gravity on dry land. If you weigh 100 kilograms at sea level in São Paulo, you'd weigh about 99.3 kilograms at the top of Huascarán. It's a small difference, but it's real and measurable. For elite athletes and mountaineers, this slight reduction in gravity can actually make a difference in performance and energy expenditure. Scientists from Peru's Geophysical Institute have confirmed it with high-sensitivity gravimeters. This is one of the points of lowest accessible gravity on Earth's surface. It's also one of the most hostile places on the planet, with temperatures dropping to -40 degrees, violent storms, and air containing only half the oxygen you'd find at sea level. Our next stop takes us deep into the Indian Ocean, to the site of the largest and most mysterious gravitational anomaly on the planet. Spanning over 3 million square kilometers, an area larger than India, this is the Indian Ocean geoid low. Here, the sea level is about 100 meters lower than it would be if gravity were uniform across the globe. Yes, you heard that right. The ocean literally sinks because gravity is weaker. This massive dent in the gravitational field has puzzled scientists for decades. It was first discovered back in 1948 by Dutch geophysicist Felix Andries Venning Meines during submarine expeditions. But it wasn't until gravitational mapping satellites came along that we understood its true, immense scale. For years, the origin of this anomaly was a complete mystery. Theories ranged from unusual mineral deposits on the ocean floor to variations in the density of Earth's mantle. Some suggested it was the scar from an ancient collision of tectonic plates. Others thought it might be a remnant of geological events from the Mesozoic era. Then, in 2023, researchers from the Indian Institute of Science in Bangalore finally offered the most convincing explanation to date. Using sophisticated computer models that simulated the movement of Earth's mantle over 140 million years, they uncovered the true culprit: low-density mantle plumes. The story begins about 120 million years ago, when the supercontinent Gondwana started to break apart. The Indian tectonic plate separated from Africa and began its epic journey toward Asia, a voyage that would eventually create the Himalayas. As the Indian plate moved north, it slammed into and slid over the ancient Tethys plate. This older, denser oceanic plate began to sink into Earth's mantle in a process called subduction, diving like a cold sheet of metal into a sea of hot, viscous rock. And here's where it gets interesting. As these cold, dense plates sank, they disturbed enormous convection currents in the mantle. These disturbances created channels for hotter, less dense material to rise from near the core mantle boundary, almost 3,000 kilometers deep, in giant plumes. These hot mantle plumes are significantly less dense than the surrounding mantle. Imagine oil rising through water, but on a planetary scale and over millions of years. As these plumes ascend and spread out beneath the oceanic crust, they create a mass deficit. Less dense material means less gravitational attraction. The Indian researchers' computer models perfectly replicated the shape and intensity of the observed gravitational anomaly. They showed that these mantle plumes are still active today, maintaining this gravitational hole. Simulations suggest this structure might even persist for tens of millions of years into the future. This discovery is profound. It shows how geological events from our planet's distant past, like the breakup of Gondwana, continue to shape our world today. It also reveals the dynamic nature of Earth's interior. The mantle isn't a static mass, but a constantly churning, active system. For navigators and scientists, this anomaly has real-world consequences. The change in sea level affects ocean currents, which in turn influence regional climate. GPS systems and satellites have to account for the gravitational variation to ensure accuracy. And for submarines and oceanographic equipment, the unusual seafloor in this region presents unique navigational challenges. The Indian Ocean and Hudson Bay are just the most dramatic examples. Our planet is dotted with smaller gravitational anomalies, each with its own fascinating geological story. The Andes mountain range, for example, creates complex gravitational variations. In some areas, the enormous mass of rock increases local gravity, but in others, particularly where vast plateaus exist, the combination of high altitude and thick crust results in reduced gravity. It's a three-dimensional puzzle where altitude, crustal mass, and mantle density interact in surprising ways. In northern Chile, there's a particularly intriguing anomaly associated with the Atacama Desert, the driest place on Earth. Here, the absence of water erosion over millions of years has preserved ancient geological structures that create unique gravitational patterns. The combination of deep tectonic faults, dense mineral deposits, and the specific geometry of the Nazca Plate is subduction, produces a gravitational field that varies dramatically over short distances. Greenland presents another fascinating case. Beneath its vast ice sheet, which in some places is more than 3 kilometers thick, the crust is also depressed, creating gravitational variations similar to Hudson Bay's. But here, the weight of the ice continues to push the land downward. As global warming melts this ice, the land will slowly begin to rise, and the region's gravitational field will change over the coming centuries. It's a real-time geophysical experiment we're observing as it happens. The GRACE follow-on satellites launched in 2018 are currently monitoring these changes with extraordinary precision. They can detect gravitational variations equivalent to about 1 centimeter of water level change over an area of 300 kilometers. This sensitivity allows scientists not only to map the gravitational field, but also to observe how it changes over time, revealing movements of groundwater, glacier melting, and even major earthquakes. In the Pacific Ocean, there are several superswells, regions where the mantle is abnormally hot and less dense, creating areas of reduced gravity. These structures are associated with volcanic hotspots like Hawaii and French Polynesia. They're windows into the deep processes occurring at the boundary between the mantle and Earth's outer core, almost 3,000 kilometers beneath our feet. Now let's return to those gravity hills we explored at the beginning, the mystery spots and magnetic hills of the world. Although they're not real gravitational anomalies, they teach us something profound about the nature of human perception and why we're so easily deceived. Our sense of balance and orientation depends on 3 systems working together: the vestibular system in the inner ear, which detects acceleration and rotation; proprioception, which tells us where our limbs are in space; and vision, which provides cues about our orientation relative to the environment. At a gravity hill, these systems conflict. Your eyes see what appears to be an upward slope, based on the visual cues around you. But your vestibular system, which responds to the true direction of gravity, says you're level or slightly tilted downward. This sensory conflict creates the powerful illusion. Neuroscience research shows that when our senses conflict, the brain tends to prioritize vision, especially when visual cues are strong and consistent. This is why virtual reality simulators can cause motion sickness. Your eyes see movement, but your vestibular system doesn't detect corresponding acceleration. One of the most famous experiments on gravitational perception was conducted by psychologist Adalbert Ames Jr. in the 1940s. His Ames room created illusions so powerful that people appeared to grow or shrink as they moved through it. The secret? Carefully designed distorted geometry to trick our brain about the true dimensions of space. Today, these principles are used in theme park design, architecture, cinema, and virtual reality. Disney is famous for using forced perspective to make castles appear taller than they really are. Filmmakers use tilted rooms to create impossible effects without computer graphics. And VR developers constantly struggle with the challenges of creating immersive experiences that do not deceive our vestibular system to the point of causing nausea. These illusions raise deep philosophical questions. If our senses can be so completely deceived by relatively simple environmental setups, what else about our perception of reality might be wrong? To what extent is our experience of the world a construction of our brain, rather than a direct reflection of objective reality? The story of gravitational research is far from over. In fact, we're entering a golden age of discoveries about how gravity shapes our planet and our universe. NASA and the European Space Agency are developing the next generation of gravitational mapping satellites, which will be up to 100 times more sensitive than Grace-4. These instruments will be able to detect gravitational changes caused by groundwater movements in individual aquifers, allowing for more precise management of global water resources, critical in a world facing growing water scarcity challenges. One of the most promising applications is in earthquake prediction. Researchers have discovered that major earthquakes are preceded by subtle changes in the local gravitational field as rocks deform under increasing stress. Detecting these changes with sufficient advance warning could save thousands of lives, providing crucial warnings before the ground begins to shake. Gravitational monitoring has also become an essential tool for understanding climate change. By measuring changes in the mass of the Greenland and Antarctic ice sheets, scientists can accurately calculate how much ice is being lost each year. The data is alarming. Greenland is losing approximately 280 billion tons of ice per year, while Antarctica loses about 150 billion tons annually. Gravitational mapping technology is also revolutionizing our exploration of the solar system. NASA's Grail mission mapped the Moon's gravitational field in unprecedented detail, revealing massive structures buried beneath the surface, possibly remnants of ancient collisions. Similar missions are planned for Mars, Venus, and even some of Jupiter's and Saturn's icy moons. And then there's the revolutionary field of gravitational waves, ripples in the very fabric of space-time caused by cataclysmic cosmic events like black hole collisions. Detectors like LIGO and Virgo have already observed dozens of these events. The future LISA Space Observatory, planned for launch in the 2030s, will detect gravitational waves of even lower frequencies, opening a completely new window to the universe's most violent events. These observations are testing the limits of Einstein's general relativity theory. So far, general relativity has passed every test with flying colors. But subtle anomalies in galaxy rotations and the universe's expansion suggest there may be more to the story. Dark matter, dark energy, or perhaps modifications to the theory of gravity itself at extremely large scales. These are the frontiers where fundamental physics will be redefined in the coming decades. Our journey through places where gravity doesn't work like it should has taken us from the sequoia forests of California to the depths of the Indian Ocean, from the icy peaks of the Andes to the Arctic vastness of Canada. We've seen illusions that deceive our senses and real anomalies that reveal the deep processes shaping our planet. The gravitational illusions, the mystery spots and magnetic hills, teach us humility. They show that our perception of reality, however convincing it may seem, is just an interpretation constructed by our brain from imperfect sensory signals. What we perceive as up or down, heavy or light, are not absolute truths but relative concepts that depend deeply on context. The real gravitational anomalies, from Hudson Bay to the Indian Ocean, reveal something equally profound. Earth is a dynamic system, constantly reorganizing itself in response to forces operating on timescales that defy human comprehension. Hudson Bay's depression is an echo of an ice age that ended 10,000 years ago. The Indian Ocean's gravitational hole is the result of events that began 120 million years ago, when dinosaurs still walked the Earth. But perhaps the most important lesson is this: gravity is not just a force that keeps us stuck to the ground. It's a tool, a measuring instrument that allows us to see inside our planet, through kilometers of solid rock, to the hidden processes in the mantle and core. It's a time window that preserves records of ancient geological events, and it's a bridge connecting the smallest movements of groundwater to the most cataclysmic events in the cosmos. As our technologies become more sensitive and our models more sophisticated, we'll continue discovering new places where gravity doesn't work like it should. But now, we understand that each anomaly is a clue, a piece of the giant puzzle that is our planet and our universe. Next time you feel the firm pull of gravity keeping your feet on the ground, remember, this seemingly simple force is anything but uniform. It varies from place to place, telling stories of ancient ice ages, colliding continents, and plumes of hot rock rising from the depths. Gravity is the invisible signature of our planet's history and structure, a map written not in lines, but in subtle variations of force that pull everything toward Earth's center. As physicist Richard Feynman once said, nature uses only the longest threads to weave her patterns, so that each small piece of fabric reveals the organization of the entire tapestry. Gravitational anomalies, whether illusions that reveal the limits of our perception or real variations that expose our planet's deep processes, are threads in this cosmic tapestry. And each one invites us to look closer, question deeper, and marvel at the extraordinary complexity of the universe we call home. Thank you for joining us on this journey through places where gravity defies our expectations. Keep questioning, keep exploring, and keep marveling at the mysteries of our extraordinary planet.